Hello, everyone. I'm Sebastian and this is Jussi Knuuttila from Redlands. We are talking about trials evolution. This is a technical post-mortem. We are not going to discuss about some design decisions or things like that. These are basically, we are presenting first the problems. I will talk about those, and Jussi will later discuss about our new ideas how to solve these problems that we faced during the project. Redlands has been founded in 2000. We created first some small games for internet web browser and Java. At some point, the TV games were big in Finland and around Europe, so we were creating some TV games as well. Then we moved to handheld games for Nokia and Gates and some PlayStation Portable and Nintendo DS games as well. After those games, we started to focus on our own brands, like Trials brand was the biggest one. So we started at first of creating a PC version of the Trials web mobile game. And then we moved the same brand to consoles, and then back to PC. We also, at the same time, we created a lot of smaller mobile games for Android and iOS. We were acquired by Ubisoft 2 years ago, and now we are creating the Trials Fusion project for both next-gen consoles, Xbox 360 and PC, and then we have a Trials Frontier game also coming for mobile devices. Trials Evolution is basically a physics-based motorcycle racing game with some platforming in it. It was released for 2012 for Xbox Live Arcade on Xbox 360 console. We got a lot of good press, and the game was really well received. The game was released later for PC on 2013. Yeah, now I'm going to go through the code base and all our technical stuff. Yeah, the game it's basically our engine, and the game is lots of C++. It's a traditional object-oriented design, and we have a custom engine that is completely built inside Redlands. In addition to our engine, we have integrated the Bullet physics engine. It's an open source library, and we have custom optimized it for the consoles that we are using. In addition to that, we have in-game UI is programmed completely in Flash. And then we have a custom visual scripting system for the levels that the level designers are using. And they are using that to script all the animation, all the ending sequences, and all the interesting part of the levels. So we are basically running a lot of scripted code, a lot of cheat code, and a lot of native code in the same time. We had a lot of technical challenges in the project, and the main reasons for these technical challenges were some really that the game was demanding in many levels. The first was that we aimed to 60 frames per second constant frame rate, always. Not 90%, but always 60 frames per second. And the second biggest one was that we didn't want to have limited user-created content capabilities. We wanted to give all the same tools to our users that we used in-house. So we wanted the user to be able to create exactly the same kind of levels, exactly the same kind of animations, triggers, everything that we used, so that the users would create exactly the same kind of content, no limitations. And that was really important for us. The third one was physics simulation. Our system is really physics-based. Everything is physics-based. The bike and rider are completely physical entities. They have connected with joints, and it's really, we don't like hard code or bike dynamics, but they are based on the physics engine parameters. But it was really hard to make it deterministic because our system is based on, our replay system is based on input recording from the controller. So we have to, every time we input the same control inputs, it needs to be identical. And this has a lot of complications because we are fully multi-threaded and we cannot, and of course there are a lot of floating point calculations, things like that we need to do in the same order, because otherwise those rounding issues will pile up and we end up being undeterministic and things will break. So that was a huge thing in the project as well. Then in Trials Evolution we changed from small indoor environment to a huge outdoor environment. And the game world is so much bigger, and the view distance is so much bigger, and the data sets are so much bigger that we started to stream everything. In our old small games, we just loaded everything to memory at the game startup, and it was fine, it was easy. But now we are basically streaming everything. And then we had a lot of programming challenges because the team size was growing, and we didn't have enough quality control in all the stages of the project. 60 frames per second was really important for the gameplay. It's basically what we wanted, that it always has to be 60. And we want it to be like that because the game is highly physics-based, and it's basically a loop of like you are monitoring the game, you are checking what's happening in the game, and the physics is like really fine-grained, and you have like really fine details in the obstacles, so you have to react really fast. And if the frame rate fluctuates, it's really hard to play optimally. And our like leaderboards are really competitive. They can be like 100ths of seconds or 1,000ths of seconds between, like in top 10. So it's really important to be that the game is really always running at 60, and always the gameplay doesn't, because otherwise the gameplay will suffer and the players will complain about it. And that means that we have to every frame needs to complete under the 60.6 milliseconds all the time. So the average, of course, must be much higher, because we never want to spend more time than that in a single frame. And that's really the limit is really low for such, like for the current generation consoles that are not as powerful. They are 7-year-old hardware basically. The user-created content was, and for the Trials Evolution, we wanted to expand the user-created content a lot. In Trials HD, you could basically share with your friends only, and you could send them manually, and you didn't have this kind of huge community around the game. In Trials Evolution, we have this kind of track sharing server that basically everybody can download their tracks, upload tracks, their download, they can rate the tracks. It's basically somehow similar than YouTube and other services, that you have like a lot of, you can have feeds with different kind of tracks, and you have this kind of features, and you can search, and then you can do lots of, like, it keeps the community together. And that has a lot of limitations, because we wanted to have the same quality of user-created tracks, but then we want to share them with players, so tracks must be small, and because otherwise the server platform will completely break down because the high bandwidth cost. And for us, it was really good that we could create high-quality level design tools inside the game. At the same time, we wanted to have like one tool set so that we could use the same tool set for our level designers and for the players. So at the same time, we could basically test the tools with our designers that they were working well, and then give a good tool set for a user. And that also allowed us to spend more time polishing the tools, and that also helped our internal level designers, because we had to make it like so easy to use that normal player could use it. Yeah, in normal game development project, you basically are designing the tools for a professional. A professional can use a lot of different kind of techniques to optimize these kind of levels and these kind of environments. Usually the tools are, you create the content offline, and then you are baking a lot of stuff. For example, usually you bake global illumination using light maps or some probes and some other things, and you are calculating some of the visibility information and things like that on the tool side. And you are storing it, and it's easy to load, and you don't need to process it on runtime. But that kind of creates it creates a huge data set. And we are streaming all our data from, or we are loading and sending those user-created levels over an internet connection to a server. So they must be really small. So we cannot use like megabytes of baked data for every level. So basically everything needs to be real time. So we cannot use a lot of baked information in the levels. One other thing that we are not, our tools are targeted for non-expert users. Our players are not professionals in track design or level design. So we cannot use these kind of advanced techniques like the manual placement of some light probes or some occlusion meshes or some portals that only like advanced artists or advanced designers know how to use. If we use this kind of techniques, like huge majority of the player-created tracks will run slowly, they will look bad, there will be graphic glitches, issues, because they don't know about those techniques. So we have to do everything manual, automatically, and we need to make it so that we don't need to, and everything just works. The engine itself optimizes, the engine itself works properly in all cases. And we need to assume that the content is basically bad, because the players don't know how to create really like optimal streamlined content. They don't know about the technical things of the console that well as we do. But that was still a pretty good thing for us as well, because some of our level designers they have like gamer roots. We recruited a lot of players who created the best levels for Trials HD for the Trials Evolution project. And also for the Evolution we created for the DLCs, we recruited some players who created good levels for the base Evolution game. So it was easy because they could start using the same tool set and creating some official levels. And that was also good for community, because we discuss a lot with the community, and they respect the players inside, and if they can create some official levels as well, then it's a huge boost for the community. And that's what basically the best creators, they always want to do. Yeah, now more about the technology itself. The object-oriented design of the engine was like based on the old things that we done for the old games. But for the new game, we had so much more objects. The game world was so much larger that it started to, like, there started to be problems with memory usage and with the processing cost of having lots of objects. And how our levels are created is a big problem itself. Basically, if you have a professional creating levels offline, you are modeling the walls and you are modeling a lot of stuff, and you are basically the artist can make an optimized version of some background or some like walls or some big structures. But in our case, we just had these small objects. A player could use them, could rotate, could place them anywhere they wanted, and basically our walls and some big structures in background. If you have a castle in background, it was created from like thousands of small objects. And that was a big problem, because, of course, if you place thousands of objects, you need to process thousands of objects, and you need to draw them, and you need to store them in memory. So that was a problem. Then also, we moved to a lot of like state-of-the-art techniques. Like all our texturing in Trials Evolution is using virtual texturing. So we are basically streaming, analyzing the screen, what texture surfaces are visible, and only loading the texture data that we need for the current screen. Of course, we need to predict what is going to be visible in the next frames as well. But that technique is really good for that. You don't need to you can use a constant amount of system memory to have any amount of detail you want. That's really like good for artists because they don't need to think about how to like manage the budget of the textures, how much textures I can use in this level, this area. Do I need to have some loading time here or some loading screen, or when I move to an area to another? Because this system automatically analyzes and streams everything, and it only keeps a small amount of texture data in memory, always. It never fluctuates. It doesn't allocate dynamically any memory. So that's good for technology, and that's good for artists. But of course, the virtual texturing itself is a really complex system, and it needs to optimize a lot of things, and it creates a huge, like big data structures that need to be created offline for the tools. And those dependencies add up. Previously, you could just use like every texture would be like separate one, and now you are combining these like huge like data files that have all the streaming data, and it's hard to like partially update them and keep everything intact, especially if you have a big team and everybody is working at the same time, updating assets and content and project. So that's a problem. And it was also technically a hard system to use because there was only a few persons who actually understood the system, and if there was problems, then the couple of guys need to always fix the same problems. In addition to virtual texture, we started to stream all our mesh data, terrain data, material data, everything. So basically, that wasn't as big problem, but of course that uses the same hard drive capacity. So we ended up with some popping in some places, and of course we need to develop some new systems to prevent the popping to be visible. So that required a lot of new technical stuff. A big problem with the PC port especially was that Trials HD was a completely Xbox 360 game. We had a multi-platform engine before that because we were creating multi-platform games for those mobile consoles. But of course, we created like a full game and then another game only for Xbox 360. So basically, we didn't have a working multi-platform code base anymore. It was okay, but it wasn't like fully supported. At the beginning of Evolution, we restored some PC functionality so that we could basically debug on PC and do some simple things, but it was not feature complete. Because of that, we had to do most of the development on the console. And on the console, you need to, of course, copy the data always, and you need to build the system, and you need to create your data packs. I earlier said that we had these kind of huge big data pack files, and that's a problem because if you make some small changes, you need to update a huge amount of data, and it of course takes time to copy things around. So our iteration time was not that good in the project. With the compilation time, we also had problems because the whole code base was really monolithic. We had this kind of offline toolset, and then we had this in-game, and they use the same technology and same tools, same libraries, and basically we didn't have any like these small kind of tools that could use to convert some mesh or convert some texture, or some like command line tools or some like easy to use tools. We just had these monolithic like two binaries. The problem was that our code base was so it wasn't modular enough to do these kind of small things fast enough. You had to always initialize the whole engine and everything, and it was really hard to do any kind of small tools and small like to improve those because the architecture was like that. And it was also really hard to test. We couldn't do proper test projects because everything was too hard to initialize in test projects. So that's really hard if you need to make thousands of test cases and test projects, and if you need to initialize whole the engine and everything for every test case, then of course, the running of the test becomes slow, and it becomes really hard to actually write the tests. So that was a really big problem. So basically, we didn't have any automated testing. We had like some like a few cases for some isolated libraries, but most of the we didn't have like automated unit testing, everything on the code base. So that caused some problems, of course, and because the manual testing was so slow, we had to copy data, we had to test on Xbox 360, we had to actually start the game, load the game. With a big game, like we had a 2 GB image at that time, it took a lot of time to load it and start the levels and test everything. So that took so much time that it created a lot of inertia for the testing. So basically, people didn't test as much. They it's just a small change. It cannot break anything, and they committed. And that creates a lot of problems in the end. You will have some small bugs that are not visible anymore, and they pop up, and that's not a good way to do. You need to make testing easy in order to actually have some testing. And then of course, because I said about the monolithic system, it was slow to debug, slow to start up, slow to compile. So every time you need to switch to debug mode, and you had to compile again, and then it took a lot of time. So we had a lot of small code issues. We didn't have that much at the beginning of project, but as we had these kind of problems, there was more and more of these small issues and bugs that were overlapping and really hard to fix at the end. And at the start of the project, we had this kind of huge problem that we didn't actually, we allowed people to write warnings in their code. And at this halfway of the project, we had a lot of warnings there. At some point, we decided that, okay, we are not going to have any more warnings. And we spent like 1 week to fix all those. Because there was some cases that people were writing code, and there was some warnings that the warning actually said that there will be a crash bug in here. But you couldn't notice them because there were so many warnings coming in of the project. So that was unacceptable for us. In the future, of course, if you have a better code base, if they're fine-tuned for our next game, of course, we are thinking about using static analyzer in many cases, because the more you get, more warnings you get, more information you get on compile time, the better. You can catch the bugs earlier, and it helps at the end. And then we had ushers as well. In the same way than warnings, at the beginning of project, there was some issues that some ushers were firing, and at some point we had a lot of ushers firing, and they were just like, people were writing ushers for some like warning purposes that this might be some content issue, and this is not. And there was a lot of ushers, and people just couldn't like click and continue everywhere. So they used this kind of ignore all ushers and functions that we added at the last project. It felt okay that if you have some assert and you have some like really high priority task, that you could ignore the asserts and code it and be productive that way. But it created a lot of issues, because if you are not like forcing the developer to fix the asserts, the asserts will pile up, and that's a big problem. It's much better just to like force people to fix. If some assert fires, you need to fix it immediately, and it's like high priority, and you file a ticket to your bug tracking system, and somebody solves it immediately. Yes, our multithreading model next. We used this kind of really simple multithreaded model. It was from Trials HD when we started working on Xbox 360. It was basically our first multithreaded game design or engine design. We split basically all our big tasks for 1 task per thread. So we had 6 threads on Xbox 360, so we had six different tasks. We rendering physics, particle animation, UI was flash-based, like I said earlier, and some other things. Well, like virtual texture streaming was on one core. But those tasks all were hard assigned to one of Xbox 360 hardware threads. It was straightforward, but it had problems. One of the biggest problems that we noticed during the project was that this is really like inflexible system. You have lots of different kind of levels. Some level is like hard of physics. You have a lot of physics objects in some levels. If you have some physics playground level, you have a lot of physics there. If you have some level that has a lot of view distance, you might have a lot of draw calls. And if you have some other that has might have a lot of sound effects or might stream more data or have more particles, for example. But in our case, always the slowest thread was what limited our frame rate. So if you had one area that has a lot of physics, you need to optimize it until the physics runs at the 60 milliseconds. And if some other place, that in that same place, if the other threads would be basically idling and have like not much to do, they couldn't help the one thread that was a bottleneck. So that was a good thing if you optimize the levels. If you spend a lot of time to like basically add some graphic object here and here, because this place is not graphics object limited, and now I can add more physics here. But it's a pain for like level design, and it's even a much bigger pain for our users, because the users are using the same tools and they don't understand that if they remove some object, the frame rate doesn't improve because that was not the bottleneck. The bottleneck might be a physics or might be some other thing, and they don't understand why they do some kind of optimization that they think would be logical, but it doesn't help at all. And we had even bigger problems when we started to port that system to PC, because PC you have 4-core processor, you have 8-core processors, and you have 2-core processors, and even 1-core. And if you have like 6 threads and you have 4 cores, it's really hard to like balance them properly, because you have 6 different things, and you have to, one thread might take 1 and one might take two processing tasks, and it's unevenly balanced. So that was a big problem on the PC porting. In general, we also had all these kind of basic concurrency problems with mutexes, things like that. People had to manually do synchronization points, and if you are doing 6 threads and they are doing all different things, then it starts becoming hard, because you have so many small things and you don't know about all the synchronization points, and then you either have like, you have 2 kind of problems. If you don't have proper mutexes, proper like synchronization, then you have some data corruption and some threading problems, and it will not show all the time. It might show once a week as a crash bug that you don't, why this data is corrupted, and it's really hard to track and really hard to fix. Also, if you use too much synchronization primitives or they are too broad, then you are having some kind of, you will usually have performance problems, because you will need some data and some other is using it, and that thread must stall because there is nothing else a thread could do. So that's a hard thing to solve with this system we used. We had to also do for some things like scene graph that was used regularly every frame all the time. Synchronization would be too performance insensitive for that, so we had to do something. We had to add a synchronization step between all the frames, and it was basically a single-threaded step, and everybody was waiting just to like update structures that we could use some structures without synchronization. Like I said earlier, the object-oriented programming was a big thing in the project. It was okay for a small data set, but when we moved up with a bigger, larger world, and lots of like these objects started to become more and more like big and clunky, and we had this kind of and then you have the same problems that you have in all games, that you have some kind of monster classes appearing, like the player class or track class or something like that, and it has like 1,000 or maybe 10,000 lines of code, and it's really hard to debug and test and assure that it actually works. with our case, our object-oriented inheritance, we had problems with this kind of object-oriented layout of the system, because basically inheritance and object-oriented structures are compile-time stuff, and you have to, if you are inheriting stuff, you have certain kind of limitations, and you can break these limitations by multiple inheritance, but everybody knows that that's not usually a good idea. So we had this kind of limitations, and we tried to solve them by adding some extra stuff and extra data to the objects, and just to have everything we needed on these objects. And they easily become big, and you don't combine. You have excess data for objects that, for example, if you have an object that don't even move in that level, you need to spend extra resources on those and extra memory on those, because it's really hard to slice the object in a way that you don't need this kind of data, and keep the systems generic enough at the same time. And if you have a lot of objects, you will have a lot of with the objects, when you are processing these big objects, you are usually, when we have the 6 threads, we are processing different things in different threads. And of course, every CPU core has its own caches. So if you are processing only a physics part of an object in one thread, you are only taking the physics data from the objects and only modifying some parameters. And some other thread takes the graphics data, and some other takes some other data from the objects. But they are not accessing fully the object. They are just accessing a small part of the object, and they are not using the full cache lines of the data. So that means that you are loading much more data to the CPU caches that you are actually using, and so you are burning a lot of bandwidth, and you are adding some extra latency and some extra waiting time for there. And that's even a bigger problem if your objects are like if you are accessing the objects through multiple chains of pointers, like it usually happens when you have objects. You don't have arrays of just pod data, but you have objects, and objects usually mean that you have a lot of pointers, and you have interface pointers and things and pointers, and you are accessing data through some chains of pointers, and then you have a lot of CPU cache stalls, and then on those Xbox 360 and the current generation consoles, cache stalls are the biggest performance, biggest thing you can do to kill your performance. And that was a problem, and that's still a problem for current CPUs. The cache misses still cost a few hundred cycles, and you can do a much more in 200 cycles that you could do in the past. Of course, out-of-order execution helps with, but it's not a good thing to use these kind of structures that are inefficient for the CPU. Okay, now we have some kind of, Jussi will present the rest of the things, all the ideas that we have for the future.
So, Sebastian just presented you with a large bunch of problems, and I hope that I can give some ideas on how we plan to solve these problems. Most of these ideas are not new in the sense that other people have thought of them before, but we thought that this hopefully will be a good collection of best practices to hopefully improve our code a lot in the future. And I'd like to start with the first thing here, because I think it's the most important. Make it easy to do the right thing, because usually when you have programmers programming, often people will tend to do what's the easiest thing. And if the easiest thing happens to be wrong, then you end up with a lot of bad code in your code base, and it's likely to cause a lot of problems. I think John Carmack said just a day ago or so that whatever is accepted by the compiler will eventually end up in your code base. And I hope in the future we can write better APIs to make the compiler hopefully not accept some of the worst kinds of things there are. And one big thing that hopefully will help us in this is the new C++ standard, C++ 11, which is being supported better and better all the time, and we have already like taken into use some parts of it and have had pretty good experiences so far. It makes it a lot easier to write this kind of like refactoring resistant code and like write loops properly, and like it's easy to pass like small callbacks without having large amounts of boilerplate code, and it's much easier to like have your memory, like avoid memory leaks by actually using these sorts of smart pointers that take away your ability to do mistakes with them, because you can't if you write news and deletes, you can easily forget to write the delete, especially if you have a complex function. But if you use these new pointers, then it's impossible for you to like forget it. We'd also like to get rid of this like huge monolithic architecture. We're planning, or we have already like started heavily splitting these libraries into smaller pieces and writing unit tests for those, so that then the testers can actually like focus on testing the actual gameplay issues instead of like imitating unit tests, which should have been already done by the programmers. And hopefully this will like eliminate lots of those like annoying small glitches that we had, and hopefully like improve code quality overall. And about code quality, we have also like taken into use these sorts of like coding standards and code reviews, and at least I believe that they have already like started helping a lot. And no more warnings are allowed, and hopefully we will also clean up all these static analyzer like warnings also, so the static analyzer can perhaps catch these sorts of things like copy-paste issues, which might not be caught by the compiler. And of course, I'd like to see our assertions like actually terminating the program, so it would force the programmer to fix those. It will be painful at first because we have a lot of assertions, but in the long run, it will probably improve the code quality by like large amount, because it's impossible for us to pile thousands and thousands of assertions. And of course, we're trying to avoid committing broken code. That's a bit of a no-brainer. Like on the larger scale of things, what I'd like to see us do is that like our new tools should allow for much shorter iteration times, both with the content and with the actual code, so that like when you're doing something, like you usually have only a limited time budget, and the more things you can try inside of that time budget, the better job you can do. So hopefully we'll like by cutting down on these like startup times and install times, and like even more so with reloading, which I'm going to be talking about, we hope that like a lot of this like useless waiting is taken out, so we can actually concentrate on getting more work done. And a big thing we plan to like try to have in the like new tools is to have this sort of hot reloading, which is popular in many modern tools now, so that when you change something, you don't even have to like close the program. You can immediately try out your new stuff. Like this is really a no-brainer for like textures and shaders and stuff like that, but we hope that we would be able to make this sort of like a plugin system where we could even like perhaps load some code without closing the program, like maybe gameplay code or something like that. Of course, if the code crashes, that's a problem, but at least it would help in some cases. And as for performance, I hope that we would be able to have like this sort of always on measurement, so that whenever like for instance in the evolution where we had these like different kinds of bottlenecks in different levels, we'd like to have a system where we always have at least some amount of like measurements enabled, so that the level designers would be able to actually see what's slowing this level down, so then they can fix the problem without like having to ask programmers for help, and this will in turn make the iteration time much faster, which will hopefully help a lot. And this also goes for stuff like tracking whether memory has leaked. And I think we already have like much of these kinds of systems, and they're starting to help. And with programming, how much time do we have left? Okay, I think I'm going to skip this one because so the big thing that we plan to do is to move into this sort of component model which is used by a lot of like engines now, like Unity, and I think many of the other like bigger engines now. So that basically instead of having this static like inheritance graph, we like compose game objects from smaller pieces of code like called components, which can be like like you can at runtime decide which objects have which components. So you don't like, for instance, if we have 1 million objects and only like 1,000 of them need to have like physics data, then we don't need to store the physics data for all of the 1 million objects, because we have had, like Sebastian told you, we have these kinds of large objects now, and most of our objects have most of the data. So now we should be able to cut out the like unneeded part of that data. And it should also help us with modularizing the actual code. And hopefully we would be able to put this kind of component data in these sorts of contiguous array buffers so that the CPU would actually like be able to utilize its like memory bandwidth efficiently, so that whenever we're processing like physics, we put all the physics stuff like next to each other, so that then we can just like load them like one after another, and the CPU cache prefetcher would hopefully eliminate most of the cache misses in this sort of like situation. And also we're not loading unnecessary data into the cache, so that well, we can make the most of the limited bandwidth that the CPU has. And in threading, we're planning to move into this kind of like a modern approach where we split all processing into these kind of smaller jobs, which are then like dynamically scheduled, so that whatever the amount of cores on that particular system, we can like at runtime allocate which task goes where. And hopefully we would be also able to use this kind of a work stealing scheduler, which is able to like really well load balance these different cores, so that each core has enough work to do, and the cores don't need to like wait for physics getting calculated or matrices being computed or something like that. I think we're probably out of time now. So apologize if I rushed a bit through the slides, but we'll be available at the Redlands booth later if you want to ask questions. I don't think we have time for that now. Or we can take one question if someone wants to ask something. Yes?
Yep.
You can probably take it.
Yeah. He asked that we had this kind of problem with draw calls and what kind of methods we use to reduce that problem. In evolution, we actually we used in our offline tools, the artist could basically combine those small objects with some larger, like you could have a pile of barrels, for example, and some kind of smaller, larger combinations, and the system would automatically like group them and do some optimizations and basically like share meshes with them. But for the new system, we are actually going to be doing things quite differently. I'm not going to talk much about that yet, but we are going to basically try to do a system that just renders whole scene with a single draw call in the next systems when we are basically doing a lot of compute share stuff and basically GPU GPU itself can determine what is visible in the screen and then generate the draws. That's still not what we are going to use in the next game, however. So that's for the long future plan. But for the next game, of course, we are going to use instancing and some other GPU techniques and to try to reduce the problem. But that's not like the ultimate solution, because we have so many small objects. We need to think about how to because we still want to keep the same kind of pipeline that our users can spam a lot of objects and they can create it, because it's easier for them. They don't need to design different kind of load levels, different backgrounds and things like that. So we want to keep that, and we need to design stuff that actually works with high amount of objects. And that's what we are aiming in the long run, but of course we don't jump into that immediately.